net force and impulse, net torque and angular impulse we completed. So I think today we can start one more important concept called rolling motion. So actually rolling motion it was there up to rolling on inclined surface, but recently they deleted the topic of rolling on inclined surface from Neet syllabus and JE main syllabus. So we can go with conditions of angular momentum in rolling motion. Up to there only we need to discuss. I think today we can complete this lesson. After that we'll see. So we can keep side heading as rolling motion. So very first when we started the lesson, we discussed about rotation of a body, like rotational mechanics of a body. And we already discussed the translatory motion of a body in classical physics part like laws of motion, work per energy, and before that kinematics and all. So now in this concept we are going to discuss like the basic definition of rolling motion is if your body is having both translational motion or translatory motion, translatory motion as well as rotatory motion, then it is said to be in a rolling motion. So here simply rolling motion is nothing but translatory plus rotate. Translatory means what? Body has to move from one position to another position. I mean, just like linear motion. What is rotatory part? Body has to change its angular position with respect to any reference line. Very basic definition of rotational motion I give in the starting of the lesson. You just go through that point, you will understand this. So now the best example of this rolling motion is example of the rolling motion is wheel of a moving car. That means if you take a situation like this, Here, this wheel will be rotating about this axis, as well as it will be going in forward direction. So it will be having velocity corresponding to center of mass, and it will be having velocity corresponding to rotational motion. That means if your body is having linear velocity as well as angular velocity, then that body is said to be in a rolling motion. Technical way if you see. So here, why I mentioned that velocity of center of mass, if the body is a rigid body, if a body is a rigid body, each and every point of it, point on it, you can say, point on it, will move with the same speed or velocity as center of mass speed, rigid body. And here it also rotates about a fixed point, so angular velocity will be there, but angular velocity of the entire body will be same. And from the angular velocity, the expression whatever we write, v is equals to r omega, that v won't be same. So velocity of center of mass is different from the velocity achieved by the rotation of the body. That's what we're going to discuss. Like if I take any very regular situation, regular condition, let's say like there is a spherical body, like a ring or a disc or a sphere, any spherical body is having both translatory and rotatory motion. Let's say it's rotating with angular velocity omega, and it is also translating with velocity vc towards right. So now if I pick any point here, if I pick any point here, this point at this instant will have linear velocity towards right, which is vc. And also look at this particular point alone. The entire body is rotating like this. Now, in terms of rotation, you see at that instant, this particular point will be having velocity due to rotational motion also, which is I'm taking here as VR. Velocity due to rotation. This is velocity of center. To understand it very clearly, one more point let us consider here. At this point, you see velocity of center of mass, of course, will be like this because the body is moving in the rightward direction. And due to the rotation at that particular instant, this point will have velocity like this. Like this point. If it is rotating like this, at this particular instant, the velocity due to its rotational effect will be downwards. At this point, velocity of the body momentarily at that moment will be downwards. That is what we. Yeah, again come to this point. One more point, bottommost point, which is in the contact with the ground. Yes. This side we see, and velocity due to rotation will be this side because this entire body is rotating like this. No, so bottommost point, if you see, it will be directed in this direction. So V due to rotation. And again, as usual, if I take one more point here, VCM and V due to rotation. So I hope you understand. So at different points of the body, rigid body, if you see, which is in rolling motion, the direction of the velocity of center of mass, I mean linear velocity or translational velocity, is same in both magnitude as well as direction. But velocity due to rotation at different points is different. It's not same everywhere because its direction is changing according to the distance from the center of the body or center of mass of the body. Magnitude value also will change. So if a body is in rolling motion, we can conclude that net velocity of any point on the body is given by root over, okay, vectorically let me explain and then magnitude I'll write, is the velocity due to rotation plus velocity due to translatory motion, which is VCM. VCM. Velocity due to translatory motion is always velocity of center of mass only. That will never change. Now, the magnitude of this net velocity will write, as we know, resultant of two vectors formula. We'll write it like VR square VCM square plus 2 times VR VCM into cos theta, where theta is the angle between the velocity of center of mass and velocity due to rotation at that particular point. Which means actually for the above situation, if we take, which means actually for the above situation, at this point, as I told you, at this point, as I told you, at this point, and at this point, if it is rotating as well as translating. So if I want to write this point's net velocity magnitude, it will be directly sum of VR and VCM, because angle between them is zero only. At this point, it will be, at this point it will be VCM will be towards right and VR will be downwards if it is rotating in clockwise direction. The resultant velocity will be here, which is root over VR square plus VCM square. If I take this point, of course, VR this side, so VCM this side, VR this side. So it will be like modulus of VCM minus VR, VNet. If VCM is more, VCM minus VR, VR is more, VR minus VCM. That condition we'll see later. And this point also, if you see, as like this point, it will be directed like this. So the net velocity of the body or net velocity of a point on a body which is in rolling motion will be always the resultant value of velocity due to its rotation and velocity due to its translatory motion. So based on these points, like the net velocity point, we can conclude which type of rolling that the body is undergoing. In rolling motion, based on the velocity of rotation and velocity of the center of mass to the point of contact of the body, we categorize rolling motion into three types that are rolling with forward slipping, rolling with backward slipping, pure rolling motion. What does it mean? Let us see. Based on the net velocity at the point of contact of the rolling body. I mean, at this point, this is what point of contact. So look at that point and see, look at this point and see in rolling motion, see clearly, if I mean velocity due to rotation, is less than that of velocity of center of mass in the point, or this point which is in contact, at point of contact, at point of contact, with respect to the ground. Understand the point very clearly. With respect to the ground, this particular point will be having tendency to slip forward. So there is a spherical body which is in rolling motion. It's rotating like this and rolling in forward direction, rolling in forward direction. But the point of contact, see it clearly, but the point of contact is having velocity in forward direction is more than that of backward direction. Then at the time of rolling, it will have the possibility to slip in forward direction. That's what we will call as rolling with slipping. If it is having the condition to slip in forward direction, we will call it as rolling with forward slipping. If it is having chance of slipping in backward direction, that we will call as rolling with backward slipping. So this condition will be rolling, rolling with forward slipping. Rolling with forward slipping. In forward direction, whatever the velocity of the point of contact is there, that is more than that of the velocity of the same point of contact in backward direction. So at that time, this is what happens. Next, if I take a situation like if VR to the point of contact is more than that of VCM at the point of contact, then so obviously backward velocity is more than that of forward velocity. Then it becomes rolling with backward slipping. In the third case, if VR is equals to VCM in magnitude, in magnitude, in magnitude, then at the same point of contact, at the point of contact, then then see, forward velocity and backward velocity of the point of contact are same, which means, understand the point clearly, the point of contact at every instant with respect to the ground will be at rest. Body will not be at rest. Rolling body will not be at rest. The point of contact, which is in the contact with the ground at every instant, because it won't be the same point at every instant, because one point will be coming and touching the ground and again going back and again rotating and coming back. So this is what frequently happening. So at every time, definitely there will be a point in contact with the ground. That point of contact at every instant is having the same forward and backward velocities, then that particular point of contact will appear to be at rest with respect to ground, which we will call as pure rolling. We will call it as pure rolling motion. Pure rolling, or one more name is there, rolling without slipping. Rolling without slipping. Rolling without slipping. Okay, three conditions. The particular point of contact point only you have to look at. And many students will have the confusion that how the body will be moving forward if the point of contact is at rest. No, this is not that point actually. You have to understand that the point of contact, whichever is going to be in contact with the ground at every instant, is having a relative motion with respect to the ground is zero. I mean, when it is coming and touching with the ground, the particular point is coming and touching the ground, it will not slip either in forward direction or in backward direction. It will just come and touch with the ground and again it will go back. So it will not slip with respect to the ground. That is the meaning of pure rolling motion. So in pure rolling motion, velocity due to rotation and velocity of center of mass both are same. VR is equals to VCM, where VR we express as R omega. Because as we discussed very starting part of the lesson, when we discussed about the Rigid body rotatory motion, we discussed about the point, particular point from the axis of rotation, which is at x distance, will be having a linear velocity because of the rotation as r omega. I mean radius into angular velocity. So this is r omega. So the condition will be like velocity of center of mass of that body will be r omega, will be equals to r omega. So if I modify this for pure rolling motion, pure rolling is very important for Neet and JE. If I modify the values according to the condition of pure rolling motion, if I take pure rolling, pure rolling motion, this point, this point, this point, and this point. Yes, yes, this will be VCM, this will be VR. But pure rolling, both are equal only, right? So this will be ru- root 2 times of VCM. Why? The two vectors are perpendicular to each other, magnitude is same. So it will be root 2 times of one of the magnitudes or root 2 times of the magnitudes. And this point will be having 2 times of VCM. This point will be having 0, 0 net velocity. And this point will be having root 2 times of VCM. So observe the point clearly. If I take topmost point and if I take bottommost point, if I classify the values of net velocity or speed, here, here it is 2 times of VC. At exactly center point, if you take, it is like this, which is root 2 times of VCM. And here it is 0. So velocity of the particular point on a rolling body from the topmost point to bottom, if you take, it will be decreasing in manner, decreasing in magnitude. The topmost velocity you can find here, and then at center it will be, and in center means when it reaches exactly the midway, there it will be root 2 times of VCM. The bottommost point, which is like point of contact, it will be 0. So you can see some diagrams like this in many reference books, like H.C. Verma, D.C. Pandey. Okay, so it will be 0. Let's say it is the bottommost point, and then if you come up a little more like this. I mean, this is when coming top to bottom. This is when going bottom to top. Because direction will be opposite. That's why I took like this. Nothing more. Direction will be opposite. Because when you see this point, net velocity will be obviously net velocity of this point will be obviously like this. So direction is becoming opposite, right? That's what I did. So the point is that in pure rolling motion, the topmost point at the instant when the point P is at the topmost level, it will be having maximum speed. And bottommost point, which is in contact with the ground, point of contact, will have no velocity, no relative velocity with respect to the ground. Okay. So see from here, this is the regular case. What are the velocities possibly there for each and every point on any rolling body? And the velocity of the net velocity of the each point and the magnitude of it. And then we calculated it for conditions of rolling. Rolling with forward slipping, rolling with backward slipping, and pure rolling, or rolling without slipping. And then we have got a conclusion for the rolling or pure rolling body net velocity at every point. Apart from this, one more note point is there in the same situation, in same concept. That note point is if any point P is at a distance x, which is less than radius you take, at an angle, at an instant you take, at an instant, with angle theta. Then, see what does it means? I have a spherical body which is in rolling motion. Let's say pure rolling motion itself. Spherical body is in pure rolling. And its radius is r, rotating with angular velocity omega, translating with linear velocity vcm. Now, if I ask, at the instant there is a point P which is making an angle 60 degrees with x-axis, with the linear velocity direction. At this instant, it will not be permanently like that. It will be keep on changing because it is under rolling motion. So at this instant, when it is making an angle 60 degrees and its distance is, let's say, some r by 3 from the center of the body. Okay, then what will be the net velocity of that particular point P? Think of it. How to do it? Think of it. If you can try and tell me the answer. Think of it. See, this point's velocity I want. So look at the situation. This particular point's velocity I want, which is at an angle 60 degrees with x-axis. So at this instant, it is like rotating like this. So at this instant, because of the rotation, it will be having velocity of rotation like this. Pure rolling on. You take it as pure rolling motion. And due to translatory motion, it will be having velocity like this. So what is the angle between them? What is the angle between these two vectors? See, this will be 60 again. And these two lines will be definitely perpendicular because this will be a tangential velocity only at every instant. And it is like radius line. So this total angle will be 90. So this will be 30. So net velocity magnitude will be VCM square plus VR square plus 2 VCM VR cos 30 degrees. And here VR is r by 3 omega. It's not r omega because tangential velocity due to rotation of any body will be depending upon the distance of that particular point from the axis of rotation. I mean, if you take a rigid body, if you want to calculate tangential velocity of a particular point on that rigid body, we apply the formula V is equals to r omega, where r is the distance of that particular point from the axis of rotation. So it will be at it is at r by 3 distance, so it will be r by 3 into omega. And we know that it is in pure rolling. It is in pure rolling. VCM is equals to r omega. velocity of center of mass will be equals to r omega at this point if you take, because that is the condition for pure rolling. But due to rotation of the body, that particular point p is having the tangential velocity equals to r by 3 into omega. So if you substitute it, root over r omega whole square plus r omega by 3 whole square plus 2 times of r omega by 3 into cos 30, which is root 3 by 2. So 2 will get cancelled. Here r square omega square common out of the root r omega, then root over 1 plus 1 by 9 plus this will be 1 by root 3. This you can simplify, will be coming as meter per, in terms of meter per second. So this is the way to calculate net velocity of any point P in rolling motion or in pure rolling motion according to the instant given and the angle that it is making with any reference line. Okay, I hope you understand. So this is all about the conditions of rolling motion and the situation of a rolling motion. In this, as I told you, there is a concept called conservation of angular momentum. Very important actually for JE aspirants. Need also either theoretical based questions from NCRT or maybe one or two mathematical oriented problems they'll ask. They asked actually previously they asked in NEET exam. So there is a chance to ask again. So let us discuss that case, which is conservation of angular momentum in case of a rolling body. It's not about pure rolling or impure rolling, it's just simply rolling. But 99% cases that we discuss in this concept also is regarding pure rolling only. Okay, so you can keep studying as conservation of angular momentum of a rolling body. Point number one, in this point number one, whenever you want to conserve the angular momentum, remember that the net torque acting on the body must be equals to zero. Because very basic condition we know that net torque acting on any body is delta L by delta T, rate of change of angular momentum with respect to. If net torque is equals to zero, that means delta L by delta T is equal to zero, which is delta L is equal to zero. So L final will be equals to L initial, because L final minus L initial is equals to 0, which is L final is equals to L initial. That means initial angular momentum is equals to final angular momentum of a body or point mass or system of masses or any rigid body, whatever it is. Initial angular momentum and final angular momentum are equal, then in that case, the angular momentum is said to be conserved, which indirectly means that the net torque acting on the body is zero. There will be no torque acting on it. In that condition only, it can satisfy the situation of conservation of angular momentum. Okay, now if we see the situation of rolling motion, generally for a rolling body, very, very important statement for a rolling body, angular momentum is given by, look at this point, angular momentum of center of mass, because the translatory motion is completely defined by velocity of center of mass. So you treat the translatory motion as a point mass motion. Like the entire body is considered to be a point mass, which is located at the center of mass of that rigid body. So the angular momentum of the translatory motion or translatory motion part will be considered to be LCM, means center of mass angular momentum, plus angular momentum of rotatory part alone, angular momentum of rotatory part. And we know angular momentum of rotatory part will be I omega for a rigid body. If a rigid body case, if I take, it will be I omega. Whether it is clockwise or anti-clockwise, based on that, this plus or minus k cap or plus or minus I cap or plus or minus j cap will be decided. But it is I omega only. And here one more important point. When you are calculating angular momentum of a translatory part, you must take the reference from the observer. I mean, with respect to the observer. And when you are calculating angular momentum of the rotatory part, that must be with respect to the axis of rotation. Very important. This is with respect to the ground, you can write with respect to the ground, observer or ground. This is with respect to axis of rotation. Axis of rotation. Let's say one example. Here one example. We take a situation that a sphere of mass m and radius r sphere of mass m and radius r is rolling and going forward with velocity of center of mass vcm, which is equals to v I cap, let's say, and angular velocity omega, and it is rotating in clockwise direction, so obviously it will be minus k cap. Okay, now see, here situation I'm framing like initially initially the sphere is rotating with the help of a shaft. Shaft means a rod, horizontal shaft about its center. And then and then suddenly, it brought into contact with ground and left. Then find its linear velocity when it comes into pure rolling. I hope you understand the question. I repeat the question. This type of questions you can find in HC Verma book. Definitely you try, because it will give you very clear cut idea about the conservation of angular momentum. It means problems. No, that such problems if you solve now, definitely you will be getting a clear idea about the conservation of angular momentum in case of rolling motion. Yeah, I repeat the question. See, there was a sphere of mass m and radius r, which was being rotated with the help of a shaft. After achieving some angular velocity omega, suddenly it brought into contact with the ground and then left, and it is started rolling on the ground. But definitely, After it brought into contact with the ground, immediately it will not be in pure rolling motion because there is no velocity of center of mass initially. So velocity of center of mass is zero. When immediately it brought into contact with the ground, the only velocity due to rotation part is there. Then it will be having some slipping in backward direction. But because of the friction, slowly the rotational kinetic energy will be converted into translational kinetic energies. So slowly it will be achieving velocity of center of mass also. So at a particular instant, it will achieve the condition which will be giving pure rolling to the body. At that instant, or at the time, or by the time it comes into pure rolling motion, what will be the linear velocity, or what will be the velocity of center of mass of this sphere? That is the question. Think of it. Just think of it. I'll give you 1 minute time. Think of it. How to solve? Initially, what was the situation? After bringing it into contact with the ground, what happens? Then by the time it achieves the pure rolling motion, what will be the condition? Just think of it. The momentum of the situation and what will be the final angular momentum. Let us see. It is in pure rolling, pure rotation, right? So it becomes I omega. Angular momentum of pure rotating body, rigid body is I omega is equals to finally means after it is coming into rolling motion or pure rolling motion, it will be having translatory motion, which means angular momentum of center of mass, angular momentum of the center of mass about the point P, about the point P now. So you need to take the entire body as a point mass which is placed here, and which appears to move like this about this point. So point mass angular momentum about any particular axis of rotation or any particular reference point will be m mass into v into r perpendicular. Yes. Okay. And it is going in rightward direction, right? So rightward direction means it appears, we discussed this point. It is going rightward direction. Its angle will be changing like this. So it appears to rotate in clockwise direction. So let us take it as minus k cap. Yeah, this side also let us take the direction. It's rotating in clockwise direction first. So minus k cap. Plus 1 minute, 1 minute, 1 minute. Hello, what we were discussing. Yeah, MV are perpendicular. So it will be appearing like in clockwise direction. So minus k cap. And about the center of mass, about the center of mass of the body, or about the axis of rotation of the body, again angular momentum will be I omega dash. It won't be I omega because initially whatever the angular velocity is there, that related kinetic energy will be changing into rotational as well as translational kinetic energy, which means some part of the angular kinetic energy is converted into some part of that will be converted into kinetic energy of linear motion. So we will write it as like initially 2 by 5 m r square minus k cap into omega. Let me write it clearly, sorry. Into omega minus k cap is equals to mv r perpendicular. So mv velocity of center of mass into r perpendicular. R perpendicular is nothing but radius minus k cap plus again 2 by 5 m r square. This omega dash will be pure rolling now. V is equals to r omega dash. Omega dash will be v by r, which is this. Okay. Now see. So this r will get cancelled, and here this is in terms of omega. Why this many are calling? 1 minute now. So let me complete it. 2 by 5 r square omega minus k cap is equals to VCM into R minus k cap plus this one 2 by 5 this value, but it will be R into VCM. So from this you can 1 R will get cancelled here. So from this you can calculate VCM. According to the conditions of directions here, we will decide in which direction the body will be moving. I mean translating. That is the condition. Okay. So conservation of angular momentum and applications of angular momentum are very important for level 2 and level 3 questions. So please do practice regarding those concepts. Okay. So let me take photos and upload in group. Wait till that.